Hello everyone, my name is Mohammed Mitwali and me, Mohammed Zil and Vashak are gonna explain how we're gonna use COMSOL to draw the figure. So here's the figure and here are the points where there are inlet and two outlets, and it's a Y-shaped. For the inlet 0.02 meter per second and the outlet are given here with the given points. Okay, so basically it's a Y-shaped figure, and the question is to calculate the percentage of the inlet flow that goes out of each branch. Okay, now we're gonna go back to the console. I'm gonna click 2D. Obviously we're gonna choose laminar. Okay, add, sorry. Okay, now obviously stationary dot. Now this is a new an empty page. Now we have to go to geometry and draw a line and just draw the figure. They said the width is it starts from 0.0, so I'm gonna set it at 0.0 and go up till 5. 1 second, zoom out. It's around here. This is 5. Okay, and then you go up by half, then you go back to 2.5, then 4.5. Okay, now this is the Y-shaped figure. Right click to form the geometry. Now I'm gonna zoom in and adjust. As you can see here, we'll have to add for the inlet the values for the inlet. Obviously choose air. Okay, and here you can see the fluid properties, inlet. Okay, now this value, it's going to be 0.02 and then complete. Now you go to the outlets, the figures are there. Okay, now my friend is gonna continue explaining the mesh part. Thank you.
Okay, now the next part we need to do is meshing. Now we have to do a multiple process to get the right mesh. First, let's start off by a standard mesh where we take the element size extremely fine, and then we do a normal mesh. Now here we get the results. If you look closer, you can see that it looks like good mesh, but if you go into the mesh and statistics, here we can observe that the number of elements is really high. However, if you look at the average element quality, it's only 0.84. It's quite high, but it's not that great, as we want it to be closer to 1. So now let's try a different type of mesh. So let's delete this mesh. Now let's create a new mesh. For this time we're going to try a free triangular mesh. Now for its size, we're going to again go to extremely fine, back to this. Now we're going to build a mesh, let it be the basic mesh. Now going back to mesh statistics, if you observe the statistics, here you can see the number of elements has greatly reduced, and you can see that the average element quality has gone up. It's more than the previous case, but again, this is a good standard mesh, but we will try and see if we can improve on this. So for our next type of mesh, we are going to try and consider, let's first initially just delete this mesh. Now let's try and add a new mesh. Now we're going to try a free chord mesh, same as before. We're going to try and keep it extremely fine. Going back to the free quad mesh, we're just going to build it. Now if you observe, the sections in the mesh, you can see it's a bit more better than our two previous cases. And likewise, if you go to its statistics, you can observe that the number of elements has decreased, and you can see the average element quality has gone up. It's very close to 1. This can be considered as a very good mesh for our question over here. Therefore, we are going to proceed with this mesh.
So Vaishak has chosen the perfect mesh for this particular problem. Before I start computing the results, I'd like to plot the graph for this mesh. For that, we'll have to right click, this plot. So as you guys can see, most of the segments of this particular meshing is in the region of 0.9 to 1, which is really good, except for a few segments in the middle, which is in the range of 0.6 and 0.7. But then again, the overall average element quality was 0.98, so we can take this particular meshing system. Now I'd like to compute the results. For that, we'll have to go to study, press compute. The system is a bit slow, so we'll have to wait for the results. Okay, it's here. So the first one we have over here is the velocity Okay, so this one's the velocity contour, and over here we can see that the inlet velocity is in the region of 20 into 10 raised to minus 3, which is 0.02 meter per second. And we can also see that along the boundary the color is blue, which is almost 0 meter per second. This is due to the no slip boundary condition, so we can understand that the fluid flow is following the no slip boundary condition. The next graph I'd like to discuss is the pressure graph. For that, we have to we'll have to change the unit to Pascal. So we can see that the inlet pressure is almost 8 into 10 raised to minus 5, which is really small. And the outlet pressure is 0, which we have given before initiating the problem. Also, in the question we were asked to discuss the pressure drop between the inlet and the outlet, and we can know that we can understand that the pressure drop will be 8 into 10 raised to minus 5 Pascal. Also, at this particular point, we can see that there is a small change in the fluid flow, and this is due to because the pressure is mainly because this is the stagnation point, and at this particular point, the pressure will be the highest, and also the velocity will be 0. The last graph I'd like to discuss is the streamline. For that, we'll have to go streamline, click the inlet, and then go to the graph. We'll have to disable this. Okay. So as we can see, the streamline is mapped in such a way that it's exactly like the velocity field, from which we can understand that the flow is, the field is accurate. So this was our walkthrough of our COMSOL analysis. We have gone through this particular problem given to us by the professor. We have chosen this particular problem because we could use this particular software. Thank you for watching the video.